Science, Queensland, and he's currently also working on his PhD at Griffith University. So hand over to Adam, please.
All right, let me just share my screen. Okay, can everybody see the screen?
Yes, Adam.
Yep, okay. Thank you very much. My name's Adam Faircloth, like Hong said. I'm a timber engineer with the Salisbury Research Facility, Queensland Department of Agriculture and Fisheries, and I'm also doing my my Masters of Philosophy with Griffith University School of Engineering and Built Environment. I'm going to be chatting about my project on developing a non-destructive evaluation system for mass timber panel systems, predominantly focusing on cross-laminated timber panels. Getting into it, so contents of my talk will kind of go through the bit of a background into the timber side of things. I haven't seen a lot of presentations on that, so that may be of interest to some of you. And then that'll flow into where we found a gap in the research and the literature and what industry's after, of where we developed this project. Then go into exactly what we're doing with acquiring vibrations of timber. The concept of it is, from what I've seen in other talks yesterday and today, fairly understood with what we're doing, but I'll touch on that part. We'll then go into the method that we've developed to conduct these tests and how we plan to validate them and what validation we've done so far, and then what we've got planned for the future. So firstly, I'd just like to acknowledge the funding for this project. So this project forms part of the Centre for Future Timber Structures hub, which is a Australian Research Council funded hub facilitated by the University of Queensland, with a number of industry partners such as Department of Agriculture and Fisheries, Hyne Timbers, ORIP, XLAM and Lend-Lease. And my supervisory team, can't forget them. My principal supervisors from Griffith University, Dr. Stephen So and Dr. Hassan Karampour. And my external supervisors from industry are Dr. Chandan Kumar from DAF, Dr. Henri Bailleres from Hyne Timbers, and Dr. Loic Brancheriau from the Centre for International Research and Development in France. So I guess the background to this project is wood-based mass panels have been widely used across the world and are becoming more readily used here in Australia. A few examples here just in Queensland are 25 King Street in Brisbane is a 10-storey tall industrial tower made completely of CLT and glulam, which Oricon occupies. Second is an apartment building that's just been finished in Kangaroo Point. And then the most recent construction announced was in Sydney, a 40-storey tall timber composite construction building that's due for commencement next year. But wood-based mass panels are forms of engineered wood products that consist of some way of laminating them together, whether that be using adhesives or some type of fasteners. These elements used in construction of multi-storey buildings, and it's quite advantageous for a number of reasons, such as they're lightweight, which means they require less expensive machinery on site to install and lift them. They're a natural carbon sink, being timber, and they've had some proven health and well-being benefits for the occupants of the buildings. So an introduction to the main element that I'll be looking into with my project, which is CLT, Cross-Laminated Timber. A quote that I like to refer to is one by a PhD graduate, Mengxi Gu, that the design of CLT and glulam composite systems is governed by their serviceability and not their ultimate strength. This basically means that by knowing the mechanical properties such as stiffness and shear moduli, we can determine the application rather than looking at the ultimate loading capacity for when they're going to break. CLT is a really good material for both wall and floor applications, but mainly used for flooring due to its large spanning applications, which it gets from that cross-layering technique that you can see in the top left figure. So The mechanical properties of these panels is determined in one of two ways currently, the first of which being an averaging or pre-manufacturing technique, which is developed by non-destructively grading the individual boards that go into the panel prior to developing the panel, and then using each of the individual values from those boards, an averaging process to determine the total panel mechanical properties. The second of which is a static testing method, quite standard, where the panel is tested under 4-point loading until failure occurs. And from that, we get a load versus displacement curve you can see in the bottom right, which tells us from that the slope, which we can find stiffness. Now, both these techniques have their advantages in terms of time saving for the averaging, but and disadvantages in terms of costliness for the static tests. So non-destructive evaluation of timber is a common technique for beams and boards, whether that be through pre-stress tests or acoustic non-destructive tests or vibration measurement tests. But no such technique has been developed by industry for mass timber panels. Research has been conducted into that area, but no technique has been adopted by industry for use in an inline rapid assessment process. So that brings us into the aim of this project, which was to develop a non-destructive evaluation system for cross-laminated timber to be implemented and installed within an inline scenario for a manufacturing facility. Within that, there's a number of subcomponents to that, I guess, question that we've come up with, or aim. The first of which was to develop a vibration-based system using surface-mounted accelerometers to analyse the vibratory response of CLT panels to impact. The second, to validate those experimental results through static tests, so by taking the full-size panel, which is at its smallest size, 3 metres by 2.8 metres, with varying thicknesses, and then validate the results we get at a full scale down to the small scale destructive tests that we looked at before. The third is to assess boundary conditions. The boundary conditions, or way in which the panel is supported and restricted in movement, are very important for these kinds of tests, especially if it's to be a rapid-based experiment. And then the fourth was to investigate a number of assumptions that we identified through literature that seem to be the cause for why industry hasn't been as keen to adopt some of these systems that have been developed. So firstly, the method that we've gone with from literature, Renee Steiger has done a lot of work into this area of non-destructive evaluation of cross-laminated timber especially, and developed this kind of multi-pronged approach of experimental modal analysis and theoretical modal analysis. So this is well understood from what I've seen in other talks, but I'll go through it briefly. Modal tests are conducted on the panel. Those results in terms of acceleration from the impulse or output and input from the impact hammer taken and used to recreate the mode shapes. And then at the same time, using the panel properties in terms of dimensions and density and material properties in terms of Poisson's ratio, we can reconstruct that panel and then simulate how it would respond to the same boundary conditions under the same impact load and compare the two. And using an optimization process, tune the elastic parameters that we feed the model to then decrease the error. There we go. So from that, the first thing that we looked at doing was to pick a boundary condition. So from literature review that we'd done, 5 to 6 standout boundary conditions were reported as being useful and able to do this kind of testing with good accuracy. What I mean by good accuracy was a 10% difference between the experimental results and the theoretical results. So from that, we decided to go with 6 different configurations, as the results from paper to paper did vary with what was being the best bet So we wanted to make sure that we were getting the right condition for the right approach. So we used air bladders, suspension straps, and in different configurations to achieve a freely supported system, and then simply supporting the panel on top of beams to give a simply supported condition, and then supporting the edges and lengths of the panel to give a simply supported and free on perpendicular sides approach as well. So from the results of those tests, we found that the freely supported conditions were by far the easiest to not only set up, but they also gave the clearest results. Although the simply supported and simply supported free condition gave comparable results, the higher modes did increase in error. And our aim is to obtain up to the first 12 modes to give us an accurate result for stiffness. So looking into the freely supported results further, we found that there was a noticeable shift in results from the airbags or air bladders, and the suspension straps, whether they were conducted on flat or edgewise testing, and found that from that shift that more testing needed to be done into the airbags, mainly for their pressure used to support the panels. Doing a pressure investigation, we found that lower pressures, that a varying pressure did cause this shift, and the varying pressure went from resulting as a freely supported system to becoming so stiff that they would act as a simply supported on point system. So from the experimental results, once we'd conducted all of our boundary condition tests, we found that the airbags in a freely supported system were going to be not only the most appropriate for industry application, but the most accurate, reliable, and repetitive in terms of repetitive rapid tests. So from there, we looked at the theoretical approach that we were going to be taking. So a known hurdle we observed in regards to this was the effect that shear deformation forces in the panel would have on results. As we're designing a system to deal with multiple thicknesses, varying from everything from 75 mils is the lowest for a 3-layer panel, up to 150 to 200x millimeters thick. The effects of shear can definitely lead to errors being introduced. So a good way I like to explain this is by considering a large book. If you were to bend that book about the center, you would get some differences in the pages wanting to shift between each other. And by restricting that shifting in the pages, by clamping your hand on one side, the book isn't able to bend as far and it feels stiffer. And that's exactly what the difference between thick plate theory developed by Timoshenko and Stephen Timoshenko, sorry, and thin plate theory developed by Uller and Bernoulli do. So Uller-Bernoulli plate theory or thin plate theory doesn't take into account shear deformation forces. And by using this theory to govern the analysis of thick plates, you get increased over-predicted frequencies and minimal deflections, which causes your panel that you're assessing to be considered as stiffer and stronger than what it actually is, whereas Timoshenko takes into account that shear deformation force. So results that we've gotten so far have been mainly on thin plates or panels that satisfy the thin plate condition, although we are looking to do and have done preliminary experiments on larger panels and are still processing the results. But the results I've gotten so far from the 75 mil thick panels have gone through the entire validation process. So they've been tested at 3 meters by 2.8 meters, and then cut from those panels, sections were cut, and those sections were tested in the bending configuration you can see in the bottom left. From the results, comparing our theoretical response, our experimental non-destructive results with our experimental destructive results, we get about an 11% difference in terms of the major direction, keeping in mind that CLT has a major and minor direction depending on the layering of the face boards being in direction of the longest length, and then a 13% difference in the minor direction, which was perpendicular to those board directions. So from those results were obtained from a set of 5 panels, and from those panels, 2 samples were taken from each panel, so a total of 10. All right, I'm getting close. So the next thing we wanted to look at in terms of sensitivity of those sizes was to see how far up we could go. The longest length we had access to was a 6 metre long billet at various thicknesses. So we tested them under the same conditions that we tested the 3 metre panel. From that, we are still assessing the results, but the panel was tested at 6 metres, then cut down to 3 metres by 2.4 metres, and then from that taken sections off of the edges. So far the results match up well in terms of frequency positioning, but pardon me, the experimental results and validation is still yet to be completed. So then moving into the assumption investigations that we've done, a number of assumptions are made through previous studies have outlined that the panels are assumed to be perfectly bonded or modelled as a whole plate, when in terms of CLT is only the faces are bonded together and not the edges. This is definitely not the case. So in collaboration with Griffith Uni and through the use of IAP studies, we've conducted a number of model investigations using ANSYS to model the CLT panels in terms of the individual boards that make up the panel, and compare that with our theoretical approach that we've used for plate analysis. Depending on the results of that, which we're yet to fully analyse, that could influence how we develop our final system and what kind of prediction techniques it uses. Secondly, with that, using modal reconstruction, we wanted to determine whether the mode shapes and frequencies we were obtaining were of the correct frequencies to ensure that our error was as small as we could make it. So we conducted modal analysis and reconstructed those mode shapes from the tests that we've done. Again, not finalised, but preliminary analysis indicates an increased error for higher modes with the ANSYS models, showing that there is a difference between the plate analysis of a whole plate and considering the panel as a individual board makeup. And for the mode shape reconstruction, so far lower modes have a nice close a small error between frequencies that were obtained for lower modes, and then as that modes increase, the error does too. So that's basically what that one just said. And then finally, the expected research outputs we hope is to develop an NDE system for industry to use in a rapid manufacturing process. The system will assist with the QA process or quality assurance within the mill, and hopefully cut down on assumptions that are being made in terms of manufacturing. Experimental analysis and testing is still yet to be conducted on thicker panels to determine validate for those thicker sizes. But so far we're pretty confident with the results we're getting from our preliminary tests that we're on the right track. Thank you for listening, and thank you to the ANSHM conference for allowing me to present, and for all the presentations that have been so far. They've all been very interesting to watch and listen to.
Yes, thank you, Adam, for your effort to make this presentation. Actually, I think yes. You know, we have heard many presentations regarding concrete and steel structures and the ANSHM application in those structures. So now with timber structures, as you can see, that timber buildings is becoming more and more popular, and also the height becomes becomes taller and taller. And in Brisbane, we have a 52-meter building, 9-story building, and in Norway, they have built a new tallest timber building of about 85 meters tall. So now structural health monitoring, you know, it becomes more and more important for timber structures as well. Again, because of the time, may I allow for one question to Adam, please? So any questions from the floor?
Yes, there's a question. I would like to ask, what would be, obviously the interest would be in developing a novel approach to do the inspections of the panels. How do you envision the end product resulting? Would it be a machine, or it would be an apparatus that would be tapping around the panel, or how do you envision that apparatus coming into reality in your view?
Yep, that's a good question. Ideally, a no user interaction interface would be fantastic. Although at the moment our aim is to just prototype a semi-automated process. So in terms of automation, what we've done is we've automated the peak detection algorithm. So when the tests are conducted, the frequency analysis is conducted automatically, and calculations will be done based on known properties of the panel. As a production site, the sizes shouldn't differ, but there will be options where they can manually enter the sizes if they are a special size. But at the moment, no plans are really in the work for a fully automated system, which would be another reason industry may not have adapted these systems in the past, is their current grading process for boards is quite automated and streamlined, whereas but CLT, especially in Australia, is quite new, and the production of it, while it is speeding up with these new buildings, is still at a level where a system like this would be well suited, at least to start with, to upgrade their QA process until a system that could be fully automated has been developed.
Thank you.
Thank you. Thanks, Adam. And if people have more questions, you're more than welcome to use the chat box to post questions. And I'm sure the two presenters, Thomas and Adam, will be happy to answer the question. So, and with that, I would like to thank both presenters for the interesting and the excellent talk, and also thanks audience for your input. And with that, I would like to close this session and move on to Tommy.